Hello everyone, and welcome back to Mitchell's Physics Review. Today we will be working on rotational momentum. Let's look at our question. A space station is constructed in the shape of a hollow ring of mass 4.5 times 10 to the 4th kilograms. Members of the crew walk on the deck formed by the inner surface of the outer cylindrical wall of the ring with a radius of 130 meters. At rest, when constructed, the ring is set rotating about its axis so that the people inside experience an effective freefall acceleration equal to g. The rotation is achieved by firing two small rockets attached tangentially to opposite points on the rim of the ring. So, first in this problem, what we can do is use the given picture and draw a little torque diagram for ourselves. We know that the force from the rockets are going to be tangential to the circle. Now these will both be useful later for our later calculations. Next, we can look at our givens. We know the radius of the circular or the cylindrical outer wall. We know the mass of the station, and we know that A is equal to G because free fall acceleration is equal to G. So, where are we going to start with this? Well, we're going to start with the equation for angular momentum. To be specific, the equation for angular momentum that is L equals moment of inertia times angular velocity. But in this problem, we are not given angular velocity, so we must substitute, which is what we're doing over here. So we know that acceleration is equal to the radius times angular velocity squared. By doing some algebra, we can get angular velocity alone, and we find that it is equal to root acceleration over radius. So, what we're going to do is we're going to plug that into our equation where angular velocity goes, and for the moment of inertia, we're going to use mr squared. From there, we plug in the mass, we plug in the radius and square it, we plug in 9.8 for acceleration, and we plug in the radius once again. Now, why 9.8 for acceleration? Well, remember, A is equal to G, and G is 9.8, so that means A must be 9.8 as well. Overall, we get that there's an angular momentum of 2.1 times 10 to the 8th kilogram meters over second squared. So, that was the first half of our problem. Now for part B. For what time interval must the rockets be fired if each exerts a thrust of 130 newtons? Well, this is where our torque diagram is going to come in handy. We know that there are two torques on the object, and both torques are causing the object to rotate in the same direction. So, now let's look at our equation. We're going to use that the net torque is equal to the moment of inertia times the angular acceleration. Like above, we said that there's two forces, so 2F, and since they're moving in the same way, they're both the same sign, or causing a movement in the same direction, they're both going to be the same sign, times the radius equals mr squared times angular acceleration. From there, we can do the algebra to get angular acceleration isolated and find that 2 times the force over the mass times the radius is equal to angular acceleration. From there, we can use the equation that time is equal to the angular velocity over the angular acceleration. Now for this, we can just use the reciprocal of angular acceleration and multiply it by the angular velocity, which remember, we found up here. So we're going to plug that back in down there. Now we know A is still equal to G, so this value right here should still be 9.8. We have the mass, we have the radius for this part, and 2, and they gave us a force of 130 newtons. From there, all we have to do is plug it into our calculator to get the time is equal to 6,177 seconds. Now, what are some common struggles with this problem, and what did I struggle with? Well, when I first read this problem, I was reading it quickly, and I missed the part where it said free fall acceleration is equal to g. Now, if you've been following along with this problem, you know that was a pretty fundamental ideal to solve and get this problem correct. So for me, what I've learned is when I'm reading these problems to take them slowly and carefully and read them completely through to make sure I have all the information. I hope that is something you take away from this problem as well, knowing that sometimes if we miss crucial information, we can't do the problem. Another thing I struggled with a little bit was substitution, which is a pretty common struggle. So for me, what I'm doing to improve that is I'm looking at my AP equation sheet and I'm working on memorizing some of those more simple formulas and how to manipulate them. I hope this video helped you a lot, and I hope you take some of my suggestions to help improve. Have a great day.